But this is cool, so you're going to want to watch. So what they're going to show you, and I'm going to actually, you guys see the mouse moving around here? Pay attention to the mouse. So this is the left lung, and this is the right lung. And this here, I'm going to pause it for just a second so that I can show you things. So this, if you guys all feel on yourself right here, this is your trachea. It connects your mouth to your lungs, okay? So your trachea runs down here in your chest and divides in two to go into each lung. So your trachea connects your mouth to the outside world, okay? And then your right, the other connection that your lung has, because the lung's job is to take air from the outside world and put it into your bloodstream. So the other job, the right heart is in here pumping, and it's pumping blood into a big vessel that leads into your lungs. And that big vessel is right here. So what the scientists have done is they took a piece of plastic here and tied it into the trachea, and a piece of plastic here and tied it into the heart. Now, what you're going to see next is that see how nice and pink the lungs are? The scientists are basically going to take a form of a bleach that's going to, something that's really destructive to the cells but leaves the extracellular matrix alone. And they pour that into the trachea and pump it through that main blood vessel. So both of these, this is what these blue things are, is these blue things are basically pumping bleach into these areas. And you see that that pink structure is now turning white. And in fact, we're about to see that the whole lung is progressively turning more white. Does everybody see that? It's becoming very uniform. You have this part still has cells at the bottom, but now they're about to show you that even that part at the bottom doesn't have any more cells. So it is just this, basically it's this almost see-through scaffold with no cells on it. And now they're going to show you growing the new lung. And I'm going to let it pan out here, and then I'm going to stop it for a second so that we can see it together. So this, you see the lung is this, it's not lung anymore, it's just that extracellular matrix. It's buried under this growing stuff that grows cells. It's basically just sugar water and it's got other food for the cells. And so you can see that it ends here, right? And the lung is buried under that fluid. Now your lung does, if you think about your lung in your body, you breathe like this, and your lung opens up like this. Okay, that's the force that your lung experiences. Okay, and your lung also experiences another force, and that's the force of the blood pumping through your lungs, pumping the blood through your lungs. And what the scientists are going to do is they're going to simulate both of those things so that the skeleton of a lung feels like the same forces that the lung would normally feel. Okay? They're going to simulate this for this little lung, and then they're going to start pumping the cells that want to become blood vessel cells. Remember how one of you told me you can sort of convince a cell to move along a certain pathway? So they're going to pump cells that want to become blood vessels through the heart part, and they're going to pump cells that think they should become the lung cell, airway cells into the airway. And they're going to try to recreate a lung. So let's see how they do. So you can see, this is they're showing you the lung now up close. Now here they're going to show you the pump that pumps blood, or the blood-like cells, through the lung. Yes, and here the vasculature is way for vessels, and this is the syringe that's going to make the lung go like this. So the lung, this little lung in there is going to feel forces. So you see how it's getting, here it's big, and there it's small. Do you see that? Getting big, getting small. Does everybody see that? So it's going like this, and the roller is pumping just like the blood. So the lung is experiencing the same forces that it would if it was in the body. And while it's experiencing those forces, they're actually pushing the cells into there so that the cells experience the forces that they would experience if they were lung. And we think, remember how you guys were saying the signals can tell the cells what to do? These mechanical signals and the signals of the matrix, that scaffold that it's on, tell these cells to become lung cells. And look, now we don't have just this white skeleton anymore. We have pink lung tissue like what we used to have. So now let's see whether we can make these lungs work. So this next video is what they're going to show you here is after a surgery. And here's the surgery. The surgery is that they opened up this rat and they did a lung transplant in the rat. So they opened the rat up, they took its lung out, and they put one of the new lungs in. And they sewed, they're going to have to do 2 sewing, right? The first sewing that they're going to have to do is to sew the blood vessel into the heart. And the second sewing is to sew the trachea into the airway. And they're going to do that and then see if this lung works. And you, I hope, are going to really think that this is something else. Okay, they've just done the sewing. This is, just to orient you, this is surgical gauze here. This is all the places where they sewed the connections, the connection to the heart and the connection to the airway. And this is the lung that is opening and closing like a real lung would. And the rat is living while they're doing this. This isn't like in like a chamber. This is a real rat that is actually breathing while they're doing this. The rat has some medications to make it sleep, but the rat is actually breathing. And you can see that the lung, sorry, I was talking and missed out on what I wanted to show you. Okay, so you can see as it starts to open up here, it has areas of bruising. It doesn't look like it's so healthy as they initially start working. And then you'll see this area up here actually start working. You see how it's opening up now? Whoa, there it goes. That's the lung opening up and starting to become healthy. And about 10 minutes later, the whole lung is healthy. Blood is flowing through it. It's opening and closing normally. And this is what your lung would look like if we opened you up. This is the healthy-looking lung. So your idea to just give Sohini new lungs worked. And thanks, Kate, for donating the scaffold. And you breathe so much better now.
Yeah. Can you do less with only one lung, though?
Oh, actually, no. It turns out you pretty much only need one lung. Yeah. I mean, if you want to run a marathon, you're going to do better with 2. But yeah, no, they're just showing you where the connections work. They're just showing you where the sewed connections work.
That was awesome.
So this is thanks for being nice to me because it is a big class. So look, the last thing I want to talk about is and let's see, actually we've got 10 minutes now. Okay. Did anybody have questions they wanted to ask me about this, by the way?
Has it ever been successfully done on a human?
No. But that's so she asked, has it ever been successfully done? So let me tell you what has been successfully done. People have started to do healing of large burn wounds with skin stem cells. I don't exactly know where that is because it's not my thing. I'm not a skin doctor, but I can tell you in the chest area, this windpipe we were feeling here. This specialized structure is pretty simple compared to some other organs like a lung. And there is a surgeon in Europe who has actually people who have cancer or had, like if you can imagine, you got a terrible car accident and this was crushed. There's actually been some regrown tracheas. So he takes, you need a new trachea, he takes your cells and grows them on an artificial membrane and that looks like the same structure as your trachea would. And some of the cells start making cartilage, and some of the cells, I mean, it's crazy how it becomes normal. And he sewed it in. And that has been done successfully at least once, and I think 2 or 3 times. I've actually seen that person give a talk, so it is definitely moving in that direction. And you can imagine, like, kidneys, right? This is especially kidneys, because kidneys, it's pretty easy to take somebody's kidney out. Like, people do give each other kidneys. Kate, you're not really going to give anybody a lung because we don't do that in the United States. But people, we do give each other kidneys. So like if Sohina had a terrible kidney disease and you were a match for her, you can do just fine on one kidney. So you may, some of you may even know like family members or friends who donated kidneys to another person. So you can imagine you would totally solve the rejection problem if you did this, right? You just take the kidney out, you bleach away all the cells, you take that person's stem cells, you put them on the new, you get them to form a kidney just like this, and then you put them in, and then you don't ever have a problem with rejection.
But you still need a donated kidney.
You still need the structure, but one of the kids in the second class says, well, why don't we just figure out how to make that? See, like the possibilities become endless. Like he was just like, I'm going to figure out how to do that. so.
But if you can get rid of the rejection issue,
Right.
it doesn't.
It totally opens up worlds.
Yeah.
Yeah, it opens up incredible worlds if you get rid of the rejection issue. Okay, so I'm going to shift gears. So and this is like, realistically, this is probably only 10 or 15 years away. Like where we are right now with this much success in Iraq, we're really probably only 10 or 15 years away from this being real technology available in humans. Okay, so now I'm going to shift gears again. And one of the other things about where you can get the scaffolds, like this is a complex ethical issue, just like cloning is, but like pigs actually have very similar anatomic structures. So you could actually, where the issues of xenotransplantation when the cells are pretty complicated, if it was just extracellular matrix, that would be pretty easy. So, okay, shifting gears now. I can't believe you said it. Inducible pluripotent stem cells. I was gonna try to get you there, but since we're already there, the class lesson just got a lot shorter. This turns out was the subject of the Nobel Prize in 2012. So this very cool work, okay? And I'm gonna try to distill down in just a couple of minutes. You know that all the information to be a heart cell or a lung cell or a brain cell, right, is contained in the nucleus. All those cells have essentially the same nuclear structure, not exactly, but similar nuclear structure. Right? So then, when we talk about, what words do we use? Do you guys know the language we use to talk about what genes decide to get turned on in a cell? Gene expression, right, is the language we use to describe that. So certain genes get turned on, and we say they're expressing, or the gene expression for that gene is on, and certain other ones are silenced. Their gene expression is off, right? So what makes an eye cell different from a hair cell is what gene expression patterns get turned on, right? And obviously stem cells have a gene expression pattern, right? So the gene expression pattern of a totipotent stem cell is probably different than a pluripotent, right? And that's going to be different than an eye cell, right? And a nerve cell, a lung cell, and everything else, right? So if you made lists, okay, then this is actually how it gets done. It gets done on computers because the lists are massive. But if you make a list of all the genes that are turned on in a totipotent cell versus a pluripotent cell versus, you can then start comparing, well, what genes are turned on, right? Now, what a set of scientists did in Japan is just mind-boggling, is they figured out, using really complex computer programs, they figured out, we think we've got it narrowed down to a pretty small number of genes that make a totipotent cell a totipotent cell. As it turns out, it's 4. Now think about that. It's crazy. They figured out that 4 genes make a totipotent cell a totipotent cell. And then to prove that, how would you prove that? How would you prove that those 4 genes were the right ones? Turn them on. So they took your skin, a piece of your skin, and they turned those 4 genes on artificially and made it into a stem cell, and in fact made a mouse out of it. They took a mouse skin cell, it's called a fibroblast, and they turned those 4 genes on, stuck it in culture, and basically, I'm exaggerating a little bit, they made the mouse embryo in culture and then implanted it into a mouse for growing. But basically, they made a mouse out of a skin cell. And that was the discovery of inducible. That is, you turn those 4 genes on and you induce the formation of a stem cell. Turns out it's pluripotent most of the time in experiments, but you can make it totipotent if you put it back in the mouse. So this, right, this opens up crazy possibilities, because now you don't even have to, find the stem cells in your bloodstream. Right now you can just take out some cells in your bloodstream that are healthy and turn those genes on and make your own stem cell. So the possibilities for treating diseases that we, like the disease that I take care of, that we think about as untreatable, the possibilities of really transforming those people's lives are endless with this. So, like we've used up all the time. I hope you guys found this kind of interesting. And I know there could be 5 million questions. Do you have 1 or 2 that you want to ask?